In this presentation on sets, we are going to talk about the laws of set operations. Now the first law we have, it is idempotent law. So it states that we are saying that for any set A, we have the first property we have is A union A, that is equal to A, and if we are talking about A intersection A, then that is equal to A. Now we have to prove this result. So we are saying we have to prove that A union A is equal to A. So we consider this set A union A. It has the elements, we are saying all x such that x belongs to A. It is union over here. Look at this term. This is union over here. It means we will have, or we are saying either x belongs to the set A, or we are saying that x belongs to the set A. So this implies us, we are writing x belongs to A or x belongs to A. We can write it just once. So we are saying it is x belongs to A. So what we get is that this is the definition for the set A. Similarly, when we are saying A intersection A is A, so we are saying A intersection A, that is equal to all those x such that x belongs to A. Now we have intersection over here. So intersection means we are talking about AND. We have AND over here. We are saying x belongs to A. So again, we are having this AND over here. So we can write it in this way. We are saying that this is equivalent to x such that x belongs to A, and this is the definition for the set A. So we are saying these are the idempotent laws. Next we have is the identity laws. Identity law means we are saying for any set A and the universal set U, the first one is A union phi, that is equal to A, and second result we have is A intersection U, that is equal to A. So these are called the identity laws. So when we have to prove that A union phi is equal to A, it means we are considering this set A union phi. We can write it is equal to x belongs to all those element x such that x belongs to A. It is union. So we will have OR over here. Then we are saying x belongs to phi. When we are saying x belongs to phi, then phi, it is an empty set. It means that there is no meaning of this term when we are saying x belongs to phi. So we can write it in this form, that this is the set X. It is the set containing the element X such that X belongs to A, and this is the definition for the set A. Similarly, in the second case, we are saying A intersection universal set. So by definition, we have definition of intersection. We have it has all the elements X such that X belongs to A, and we have X belongs to the universal set. Now we know that the A is a subset of U. So if X belongs to A and X belongs to U, it means we are saying that X belongs to A, because it is AND over here. We are talking about all those X which belongs to the set A and they belongs to the set U. So they are the elements of the set A. So we are saying this is definition for the set A. So this is the proof of these two results. Now what we can see from this result is we are saying that phi and U are the identity elements of union and intersection of sets respectively. So as in case of numbers, when we are talking about the say real numbers, we say that a number is the identity for the real numbers. It means we are talking about there is a number A. If we multiply this number by some real number and we obtain the answer is equal to A, then that number is called the identity. Now we are saying in case of real numbers, we have A into 1 is equal to A. So we are saying that 1 is the identity element for the set of real numbers. In this case, what we are saying that phi is the identity for the union, because we are saying A union dash, that is equal to A. So what we observe from this is that A union phi is equal to A. It means phi is the identity element for union. Second case, we are saying that A intersection dash is equal to A. So what we have seen over here is that A intersection U is equal to A. It means for intersection, we have this universal set, that is the identity for the intersection of sets. Next we have is the commutative laws. So for commutative law, we are saying that suppose we have two sets A and B, then we have to prove that first A union B is equal to B union A, and second we are going to prove that A intersection B is equal to B intersection A. So to prove this result, we are talking about A union B is equal to B union A. So we suppose that there is an element X that belongs to the set A union B. We are saying that to prove this result, what approach we are going to use is, we are going to prove that A union B is a subset of B union A, and then we will prove that B union A is a subset of A union B. If both of these results hold, then we will say that both these sets, they are equal. Now to prove this first result, we are talking about this case. To prove this result, we are considering an element from the set A union B, and we prove that it is present in the set B union A. So we are saying, let X be an arbitrary element of A union B. Then we have X belongs to A union B. And this implies us that X belongs to A or X belongs to B. It is union, so we are using or over here. So what this implies us, when we are saying X belongs to A or X belongs to B, it means we are saying X belongs to B or X belongs to A. You can write it in this way. And this is, by the definition of union, we can write X belongs to B union A. So what we have proved over here is that every element of A union B is an element of B union A. We have proved that every element of A union B is an element of B union A. It means that A union B is a subset of B union A. Now to prove the second part, we are saying B union A is a subset of A union B. We are going to prove this. So we consider an element Y from the set B union A. Then we have this Y, it belongs to B union A. It means that Y belongs to B or Y belongs to A. Again, this thing, Y belongs to B or Y belongs to A, we can also write it in this form, that Y belongs to A or Y belongs to B. And this implies us that Y belongs to A union B. So we have proved that B union A is a subset of A union B. Now look at these two results. We have proved that A union B is a subset of B union A, and B union A is a subset of A union B, and this thing can hold only when both these sets, they are equal. We have similar kind of proof for A intersection B is equal to B intersection A. We have similar proof. What we are doing, we are considering an element X that belongs to A intersection B. If it belongs to A intersection B, we are saying, then what this thing means, that X belongs to A and X belongs to B. We can write this in this way. We are saying X belongs to B and X belongs to A. And this is the definition for X belongs to B intersection A. So we have proved that every element of A intersection B is an element of B intersection A. It means A intersection B is a subset of B intersection A. Next, to prove the second part, we are proving that B intersection is a subset of A intersection B. So we consider an element of, we are saying Y is an element of B intersection A. Then Y belongs to B intersection A. This implies us that Y belongs to B and Y belongs to A. We can write it in this form. The proof is similar to what we have proved earlier. So we are saying we obtain that y belongs to A intersection B. So every element of B intersection A is an element of A intersection B. So we have proved that B intersection A is a subset of A intersection B. Now, by combining both these results, we obtain that these two sets, they are equal, and this is what we have to prove. So we are saying that the commutative law, it holds for the union and intersection of sets. Next we have is the associative law. So for associative law, we are considering three sets A, B and C, and we have to prove that A union B union C, that is equal to A union B union C. So what we mean to say is that if we have to calculate the value of A union B union C, then we can adopt this procedure that we first calculate the value of A union B. Whatever answer we obtain from this, we will obtain a set over here. We take the union with the set C. That will give us the same answer if we calculate the union of B and C first and then take the union with A. We have to prove this thing. So again, to prove this result, we will prove that this set on the left hand side, it is a subset of this set on the right hand side, and then we will prove that this set on the right hand side is a subset of this set on the left hand side. So for the first part, we are saying let X belongs to A union B union C. It means we are having bracket over here. It means we are saying that X belongs to A union B. We have this is union over here, we will have OR, and we are saying X belongs to C. So we are saying that X belongs to A union B union C. This implies us X belongs to A union B. Then we have OR, we have X belongs to C. Now if X belongs to A union B, it means, what this term means is that X belongs to A or X belongs to B. And we already have this term X belongs to C. It means we are saying or X belongs to C. Now we are saying X belongs to A or X belongs to B or X belongs to C. Now we can shift the brackets and we can write the terms in this form, that X belongs to A or X belongs to B or X belongs to C. And what this term represents when we are saying X belongs to B or X belongs to C, we are saying this is X belongs to B union C, and we already have X belongs to A or X belongs to B union C. Now X belongs to A or X belongs to, for this OR we are saying, because of this OR, we can write it in the form X belongs to A union B union C. So we have proved that every element of this set A union B then union C, that is in the set A union B union C. So we have proved that these set on the left, it is a subset of this second set. Next we are going to prove that this set on the right, it is a subset of this set. So we are considering an element from this set A union B union C. We are saying let Y be the element which belongs to this set. Then this thing will imply us that Y belongs to A or Y belongs to B union C. We are saying we have this union over here, and from this union we can write OR over here. Now we have union between B and C, so we can write OR in place of this, and we get Y belongs to A or Y belongs to B or Y belongs to C. Now from this statement we can rewrite the statement in this form. We are saying the brackets in this case, they are for these two terms. Now we have shifted the bracket to these two terms. So what we obtain from this is, we are saying X belongs to A or Y belongs to A or Y belongs to B, corresponding to this OR. we can put the union sign over there. So we can write this implies us X belongs to A union B, or we have Y belongs to C. Now corresponding to this or, we can write that X belongs to A union B union C. So we have proved that for every Y belonging to this set, we have Y belonging to this set. So we have obtained that these two sets, this relation, we are saying that this set A union B union C, it is a subset of A union B then union C. Now combining both these results, we are saying we have this result, we have this result. Combining both these results, we can obtain that the equality holds between these two sets. Similar kind of proof we have for the second case. Second case we are talking about, it is intersection, that is associative law for intersection of sets. We are saying A intersection B intersection C is equal to A intersection B intersection C. So in this case, we will prove that A intersection B intersection C is a subset of A intersection, then B intersection C, and similarly we can prove this result, and then combining both these results we will obtain the final answer. Now the proof, it is similar. We are considering an element X from this set. If X belongs to this set, we have, this is intersection over here, so intersection, for intersection we can write AND. So we are saying X belongs to A intersection B intersection C. This implies us X belongs to A intersection B and C. Now we have intersection at this place, so in place of this intersection we can write AND. We obtain the expression in this form. Now if we shift the brackets, we obtain the expression in this form. Now look at these terms. We have AND over here. In place of this AND, we can write the intersection. In place of this AND, we can write this is B intersection C. And we already have X belongs to A and X belongs to B intersection C. So combining these values now, we are saying we have AND over here. Now if we put intersection in place of this AND, we obtain that X belongs to A intersection B intersection C. Similarly for the second part over here, we are considering an element Y that belongs to this set. Then we write AND in place of intersections. We write AND in place of intersections. We shift the brackets. Then we again replace this AND with intersection. Then we replace this second AND, this AND over here we have. We replace this AND with intersection. And we obtain this result. So both these results, they are similar. Both these results, they are the proof that we are talking about. They are on the same lines. And these results we are saying that for sets, we are saying that A union B, if we calculate first, then we are taking the union with C. That is equal to taking the union of B and C and then taking the union with the set A. So we are saying that this result, these are called the associative law for union and intersection of sets. Next we have is the distributive laws. So for distributive laws, we are considering three sets A, B, C. And we are proving that A union B intersection C, that is equal to A union B intersection A union C. So we are saying that in this case, the union is distributive over intersection. So again, to prove this result, we are going to prove two things. One is that A union B intersection C is a subset of A union B intersection A union C. And second, we are going to prove is that A union B intersection A union C, this is a subset of A union B intersection C. We are going to prove these two results. Then by combining these two results, we will obtain the equality. So to prove this first result, we are talking about this result. we have to prove that this element, it is a subset of this. So we consider an element of this set and prove that it is present in this set, an arbitrary element we are considering. So we are saying let X belongs to A union B intersection C. Then this thing implies us, we have this union over here, we have this union over here. So in place of this union we can write or. So what we obtain is that this implies us that X belongs to A, or in place of union we are writing or, we have X belongs to B intersection C. Now in place of this intersection we can write it as and. So we can write this as, we are saying X belongs to A or X belongs to B and X belongs to C. Now from this term what we can say, we are saying X belongs to A, or we are having X belongs to B and X belongs to C. We can write it as X belongs to A or X belongs to B, and we have another condition, that is X belongs to A or X belongs to C. So what we can write from this expression, we have or over here, we have and over here, we have or over here. So if we replace this or with union, we get it is X belongs to A union B. We have this and over here, then we are writing X belongs to A union C. Now if we replace these unions with this and with intersection, we will obtain X belongs to A union B intersection A union C. So we have proved this result, that this set, it is a subset of this set. Similarly, if we consider the element Y in this set, we are talking about A union B intersection A union C. We are saying we can write in place of this intersection that we have over here, in place of this intersection we can write and. We can write that this implies us Y belongs to A union B and Y belongs to A union C. In place of these two unions we can write or. So we are saying we get Y belongs to A or Y belongs to B, and Y belongs to A or Y belongs to C. So what this term has a meaning, it means that we are saying that Y belongs to A. In both these terms we have Y belongs to A or Y belongs to B, and we are saying Y belongs to A or Y belongs to B. So we can write it like Y belongs to A or Y belongs to B and Y belongs to C. So what we get from this is, we can write in place of, if we write intersection in place of this and, this statement Y belongs to B and Y belongs to C, it will take the form, it is Y belongs to B intersection C. The remaining part we have, it is Y belongs to A or Y belongs to B intersection C. Now replacing this or with union, we get Y belongs to A union B intersection C. So this is the distributive property of union over intersection. We are saying that union is distributed over intersection. Similarly, we can prove that intersection is distributive over union. So again, we have to prove these two results. We have to prove that one set is subset of another, and then that second set is subset of the first set. So proof is on the similar lines as we have proved in the previous case, that we will consider the element of the set on the left hand side. Then by replacing the union and intersection with or and, we can write the statements in this form. Now we can arrange this statement in this way. We are saying X belongs to A and X belongs to B or X belongs to C. We can write it in the form X belongs to A and X belongs to B. Then we have or X belongs to A and X belongs to C. Now again replacing this and with, we are talking about this and we are replacing with the intersection. We obtain the statement. We can write this statement as X belongs to A intersection B. We have or over there. then we are saying X belongs to A intersection C. Now replacing this OR with union, we will obtain the required result. And similar is the proof for this next part. Similar proof we have for this next part. We consider the Y belonging to this set on the left hand side, and then we use the properties to prove that the element Y, it is present in the set on the right hand side. So we have proved over here that this set A intersection B union C is a subset of this set. Similarly, A intersection B union A intersection C is a subset of this set. So combining both these results, we obtain the equality over here. So this proves that the intersection is distributive over union. Next we have is the De Morgan's law. So we are saying for any two sets A and B, the first condition we have is that A union B, if we take the complement of this set, then that is equal to A complement intersection B complement. So we are saying when we are writing A union B and taking the complement of whole of this set, then that is equal to A complement. This union gets changed to intersection, and we are having over here it is B complement. Now we are going to prove this result. So again, to prove this result, we will prove that A union B complement is a subset of A complement intersection B complement. Then we will prove that A complement intersection B complement is a subset of A union B complement. So to prove this first result, we are considering an element from this set A union B complement. Then we are saying this thing. This implies us if X belongs to A union B complement, it means we have X does not belong to A union B. So it is by the definition of the complement, we are saying that X is the element of the universal set which is not present in the set A union B. So we can write this as, this implies us that X does not belong to A and X does not belong to B. So this is by the definition of the union of sets. We are saying that if X does not belong to A union B, then this thing means that X does not belong to A and X does not belong to B. So X does not belong to A. If X does not belong to A, it means that X belongs to A complement. If X does not belong to B, it means X belongs to B complement. And we have AND over here. For this AND, we can replace this AND with intersection, and we can write it in this form that X belongs to A complement intersection B complement. For the second part, we are considering the element Y from the set A complement intersection B complement. Then we are saying what this thing implies, that Y belongs to A complement and Y belongs to B complement. So if we are saying Y belongs to A complement, it means that Y does not belong to A. Y belongs to B complement means Y does not belong to B, and we have AND over there. So how we can write this situation? We can write this implies us that Y does not belong to A union B. So this is again from the definition of the union of two sets, we are getting this result. And if Y does not belong to A union B, it means it is the element of the universal set. Y is the element of the universal set and it is not present in A union B. It means that Y belongs to the complement of the set A union B. So we have proved these two results, that one set is subset of another, then the second set is the subset of first. Combining both these results, we obtain that A union B complement, that is equal to A complement intersection B complement. Similarly, we have the second result. It is A intersection B complement, that is equal to A complement union B complement. So again we have, this is intersection over here, we are taking the complement, so it becomes union on this side. So again the proof, it is similar. We are saying we have to prove that one set is a subset of another, then we will prove that second set is a subset of first. So we consider an element of A intersection B complement. We are saying X belongs to A intersection B complement. Then this thing will imply us that X does not belong to A intersection B, and X does not belong to A intersection B. Then by the definition of the intersection of two sets, we have X does not belong to A, or we have X does not belong to B. Now we can write this as, we are saying we can write it as X belongs to A complement, because look at this term over here, we are saying X does not belong to A. It means that X belongs to A complement. We have, after this we have OR over there, and then we have X does not belong to B. So if X does not belong to B, it means X belongs to B complement. Now we can write, in place of this OR, we can write the symbol for union. So we obtain that X belongs to A complement union B complement. So this proves the first part. For the second, we are considering an element of this set A complement union B complement. So we are saying let Y belongs to A complement union B complement. Then this thing will imply us that Y belongs to A complement or Y belongs to B complement. In place of union, we are writing it as OR. Now when we are saying Y belongs to A complement, it means Y does not belong to A. When we are saying Y belongs to B complement, it means Y does not belong to B. And we have OR over here. And by the definition of intersection of sets, we are saying Y does not belong to A or Y does not belong to B. It means that Y does not belong to A intersection B. So if Y does not belong to A intersection B, it means Y is the element of universal set, but it is not an element of A intersection B. It means Y belongs to A intersection B complement. So we have proved this second result, that A complement union B complement is a subset of A intersection B complement. Now again combining both these results, we are talking about both these results, we obtain the equality over there. So this is the proof for the De Morgan's law.